Okay, now let's look at the step potential problem in detail. To begin with, we're going to look at the case where the energy of the particle is greater than the height of the potential step. All right. So the energy of the particle will be higher than the energy of the potential step. All right. In this problem, it'll be very useful to break the space up into two parts, region 1 and region 2. Region 1, in our problem, x less than 0, is the region where the potential energy is 0. And region 2 is the place where it has a different value, u0. Okay? Then we can write down the form of the wave function in the two different regions. All right? First, for x less than 0, the wave function should look like this. Okay? So we should have a term e to the I k1x, because the particle in this region is a free particle. All right? And well, that's the wave function for a free particle. Now, you'll notice that that would describe a free particle moving to the right. Okay? In general, though, we should also expect we might have part of the wave function that looks like a free particle moving to the left also. Both of those solve Schrodinger's equation in region 1. Okay? So we'll include a term like that in region 1. For x greater than 0, well, we might have a particle moving to the right. It's still a free particle, but its k is different because its kinetic energy is different. All right? Okay? Now, in our problem, we're imagining a particle that's incident from the left, okay? And striking our barrier. And physically, we know that that could, in principle, give us a transmitted wave or a reflected wave. And in fact, we've included terms like that in our equation so far. However, we don't need to include a term that's incident from the left, that is, one going this way in region 2. And that's simply because that doesn't fit into the problem that we're considering right now. Certainly, one could consider such problems, but at the moment, we're not. That is, we have an incident wave from the left, a reflected wave in region 1, and a transmitted wave in region 2. But we don't need to include any other waves to describe the whole problem. So this is what we have. Okay? So, if you like, this first term represents the incident wave. The second term represents the reflected wave. And the third term here represents the transmitted wave. Okay? From what we've learned about free particles, we know that K1 is square root of 2m times the kinetic energy, which here is just E divided by h bar, because in region 1, the potential energy is 0. Whereas K2 is square root of 2m E minus u0 divided by h bar, because the kinetic energy is smaller. Make sense? Here, let's think about this. I want you to just think about those different values of k so we can get some intuition about this problem. Okay, which is greater, K1 or K2? All right, well, if U0 is positive, then it's clear that K1 is greater than K2. Which is greater, the momentum P1, the momentum of the particle in region 1, or the momentum of the particle in region 2? Or if you like, the momentum of an incident particle or the momentum of a transmitted particle? What do you think? Well, remember, P is just h bar k, right? So this must be true also. How about the velocities? Which one is moving faster? Okay. Well, clearly, if P1 is greater than P2, then U1 must be greater than U2. What about the wavelengths? Which particle has a longer wavelength? Which has longer wavelengths, the particle in region 1 or the particle in region 2? That's pretty clear too, right? Since the momentum and wavelength satisfy the de Broglie relationship, it's clear that the wavelength is shorter in region 1 than in region 2, just as we've drawn in our picture. Okay? Here's some wave terminology. Oops, excuse me. Okay. The reflection coefficient for a wave, little r, is the ratio of the amplitude of the reflected wave to the amplitude of the transmitted wave. Okay? So little r is v over a. The transmission coefficient is c over a. Okay? Where a, b, and c are defined in these equations. And then in our particular case, if the incident particle is reflected, then the reflection probability will just be given by the ratio of the ratio of the squares of the wave function, because the square of the let me write down the formula and then talk about it. So the reflection probability will be b over a squared. That is, it's the ratio of the probability density for the reflected wave divided by the probability density for the incident wave. And then the transmission probability, I'll call it capital T, is 1 minus r. All right? Because the particle will either be reflected or transmitted. All right? We'll see where this terminology comes in a few minutes, but I just wanted to mention it here. Okay? And I wanted to just warn you about one thing here. The transmission probability is not equal to little t squared. All right? And there's a reason for it, and it all makes sense, but it is equal to 1 minus r. So we can keep that in the back of our minds. All right. Yeah, let's stop this short video here.